Hi, I'm John Cox, and for this public lecture assignment, I watched a lecture by Dr. Sabeta Matsumoto from Georgia Tech School of Physics. The lecture focused on symmetry, geometry, topology, and how these ideas show up in everyday materials like fabric, sewing patterns, and knitted structures. The main idea I took away from the lecture is that physics is not only about forces, motion, electricity, or magnetism. Vegas physics can also be about the structure of materials and how geometry controls the way they behave. In this lecture, the doctor used examples like symmetry patterns, sewing, and knitting to show how simple rules at a small scale can create complex shapes at a larger scale. One of the first topics discussed was symmetry. Um, for example, a snowflake has rotational symmetry. Many buildings use symmetry because it's visually balanced and structurally efficient, but the lecture helped me think about symmetry in a more mathematical and physical way. Instead of just seeing symmetry as something that looks the same, the lecture showed that symmetry can be described through transformations like translations, rotations, and reflections. These transformations help explain repeating patterns in the plane, such as textiles and surface changers. Part of the lecture that I found especially interesting was the connection between sewing, knitting, and geometry. At first, sewing a shirt or knitting a piece of fabric seems like a craft, not physics, but the lecture showed that when flat material is cut, stitched, stretched, or looped together, it can produce three-dimensional shapes. That is a physics problem because the material has to obey constraints. It cannot just bend or stretch in any random way. Final shape depends on the geometry of the pattern and the mechanical properties of the material. One important concept from the lecture was curvature. Curvature describes how a surface bends. Positive curvature is like a sphere where the surface curves in the same direction. Negative curvature is more like a saddle, where the surface curves upward in one direction and downward in another. I already had a general idea that curved surfaces matter in physics and engineering. I hadn't thought about how you can actually create curvature by changing a pattern. If you arrange hexagons, the pattern tends to stay flat. This makes sense because hexagons tile the plane very efficiently, like in a honeycomb. But if you change the number of sides in the pattern, the surface changes. Pentagons tend to create positive curvature, while heptagons can create negative curvature. This is one of the most interesting things I learned because it showed how a tiny local change in pattern can control the global shape of a material. This connects to a follow-up idea I looked into, the Euler characteristic. The basic relationship is faces minus edges plus vertices equals a number that tells you something about the topology of a shape. For a simple closed object like a sphere, that is a 2. For the shapes with holes, the value changes. In the lecture, this came up when discussing knitted shapes and how many holes the surface might have. What I found interesting is that topology is not focused on exact measurements like length or angle. Instead, it focuses on properties that stay the same even when a shape is stretched or bent. So a coffee mug and a donut are considered similar in topology because they both have one hole. It shows that physics can describe materials in ways that are not always obvious. A knitted object is not just soft because of the yarn, it is soft and flexible because of the way the yarn is looped together. The microstructure controls the larger material behavior. This is similar to ideas in civil and engineering and construction materials. In my area of study, the geometry of a structure matters a lot. A truss, a slab, a retaining wall, or a bridge all behave differently depending on how forces move through their geometry. In the same way, the lecture showed that textiles can be engineered by changing the pattern of loops, stitches, and connections. Engineers are interested in programmable materials, deployed structures, and materials that can change shape. This lecture made me think about how ideas from knitting could apply to flexible framework, architectural surfaces, protective fabrics, or biomedical materials. Instead of only choosing a material based on what it's made of, engineers could describe the internal patterns the material believes in a specific way. Overall, I found the lecture interesting because it made physics feel more visual and creative, connects mathematics, materials, and real-world design in a way I had not thought about before. I learned that symmetry and curvature are not just abstract ideas that can be used to understand fabrics, design surfaces, and even create new kinds of engineered materials. Physics is not only about explaining the natural world, but also about designing new structures and materials by understanding the rules behind shape and motion.